Today I'm going to talk about technology in healthcare. It's different than what's on the little sheet because I didn't send the slides till today, so they didn't have the title. So Richard made something up appropriate. It's good. So could we move on a slide, please? Yeah, so I thought I'd do the 3 words that describe me first. I am a technologist through and through. I'm going to talk a little bit about how I got into this career, why I love it so much. That's basically all this deck. I am a fan of slightly unusual pets. I have a snake, I have 3 cats. 2 of them are part wild, one of them is a quarter serval cat. So it's the most wild legal cat you're allowed to own, and it is a real rascal. And yeah, I love shoes. I like wearing colourful shoes. It's part of my personal brand. So if we move on. Why technology? Why do I love technology? It's really like I'm only going to do a few minutes on it. I don't want to talk about myself all this time, but basically, when I was really young, I don't know, less than 10, I think it must have been when I was about 8 that this came out. The Amstrad CPC 464, which looked like that, was our first family computer. And my uncle worked in consultancy. He built software for people, and he came round to our house and he taught me how to do something really simple. Just create asterisks on a screen that kind of fell down like snow, and it had me hooked, really. And I started learning how to program BASIC before I got to 10. Just rubbish stuff, but that was it really encouraged me, and like a family member that really wanted to help you was really important. Next, please. There is a clicker here, isn't there? There you go. I don't have to say next, please all the time. Yay. So yeah, I kept loving this stuff, and then it came to work experience time, and I decided at that point in my life I wanted to be a pharmacologist. I don't know why. They wouldn't let me work in a lab creating drugs for people, so I decided to go and do work experience on a hardware test bench. I worked with a great group of people. They taught me how to test people's motherboards and stuff that were returned. And they offered me a summer job after that, so I worked the summer there, and they bought me and gave me my first ever own computer after that group of people, and they were also instrumental in me loving technology. And I really do recommend, if you love it too, find those people that are really going to mentor you and help you and teach you about stuff. And then at 16, I got my first summer job. In fact, I worked here every summer, all the way through college and all the way through university, for a company called GEC Marconi. I worked on real stuff from that age. I was coding for GEC Marconi. I got to see some awesome things. I went down to Rochester. I sat in a helicopter simulator with silicon graphics everywhere and a helmet on. I went to a field, and we did one of the first ever test flights for this unmanned aircraft. All sorts of really amazing things that interested me too. So anyway, if you love technology, keep doing stuff early on, basically. And then a bit about who I am now. So I work for a company called BJSS. For those of you who don't know us, we're a technology consultancy. We advise and build software with our clients, like in partnership. We're about 2,500 people now. So when I joined, I think we were like 300 or 400 or something like that, and that was only eight and a bit years ago. So really gone through a lot of growth, which has been really exciting. Our beating heart is building software, and not just building any old software, building really tough software that solves really complex problems for our clients, and we love doing that. We're really proud of it. I'm quite proud of the stuff I'm going to show you here, which are some real examples of what you can do with technology in the field of healthcare in this case. We do stuff around like building software, low code, which is a new trend of like writing software without actually writing code itself. Data and AI, that's my background. I love data and AI. I joined BJSS to build that part of our business. I did run it till only a couple of years ago. And actually before BJSS, I worked in a consultancy specifically for intelligence agencies, helping them do data and AI. And cloud and platform, cybersecurity, all the things you've heard, we do all of it, and it's brilliant. We work across all these different fields, retail, public sector, the whole lot. But what I'm going to talk about today is some real use cases, some real stuff that we've done and we know in healthcare to bring it to life, what technology can really do in that field. If you've got any questions during it, I know there's Q&A later, but just shove your hand up if it's related to this or shout out, it's fine. So this is to illustrate how important technology is behind the scenes of our NHS. So the national healthcare, our national healthcare is incredible, and behind it, everything you do has technology behind it. We've been working with NHS Digital. These are the people that build the platforms and software that underpin the NHS at the back end. Not the stuff you see clinicians use, but at the back end. And you'll see all these things. I'm not going to touch on them all, but there's some amazing stats here. Spine 2 is one I love. So a number of years ago, we looked to replace what was called the spine of the NHS. This is the system that every time you go and get healthcare anywhere, whether you go to your GPs or you get or go to pharmacy and get a prescription or whatever it might be, a message with your data needs to be sent across a backbone. And that needs to be sent out to all the other systems, and it needs to collect your patient record information, it needs to know about your prescriptions immediately so you can go pick that up somewhere. That's the NHS spine. We built that, the new version of that, alongside NHS Digital, and it deals with, 3,500 messages a second, billion messages a month. It has 100% uptime for its life. That is very, very rare. This system doesn't go down. It can't go down. Clinical impact of that would be giant. So, tough problems, but amazing. It's behind the scenes. It sits there. You never know about it, but it runs it. The NHS app, we helped design and build that. You may have used that, especially over the last couple of years during COVID. Not the COVID app, that one didn't work so well. The actual NHS app, the one where you can book your doctor's appointments, where you can see your COVID pass, where you can book your prescriptions, etc. That ramped from 0 to 24 million. It is now users in 2 years. It's the most downloaded app ever on 2021 for free, the most freely downloaded app in the UK, and it's pretty cool. And then the other kind of things that you got, like COVID hit, right? Loads of technology needed to put in place really, really quickly, as did all the business change, that kind of thing. Example here, emergency department digital integration. So it used to be the case, you just walk into, and it isn't again now, just walk into A&E if you've got an issue, if you can walk. You'd walk into A&E and you get your appointment. In COVID, that would just spread COVID around because loads of people that were going in had COVID. And you might be immunely compromised, go in and get COVID from somebody else. So they had to very quickly have a kind of like booking system for A&E slots. You'd call up NHS, you'd call up the NHS phone number, they'd get a booking for you, go in at a specific time, and you wouldn't interact with other people. That system needed to be built in 3 months flat, deployed out to every ER in another month. If you work in technology, you'll know how long it usually takes to build a system like that. We are talking years. And to implement it and scale it to every single ER in the country would be huge amounts of testing. But during COVID, the reward far outweighed the risk of speeding that stuff up. And it was really, really exciting. Different way of delivering technology and software. And really, really worked really well, actually. And then finally, there's another thing. So when COVID hit, there was a piece of work done to assess who was most at risk so they could get their vaccines as quick as possible. That's actually an Oxford University algorithm called Q-COVID, and we wrapped all the software around that identified all the patients that need shielding or vaccinations quickly, and they got their vaccinations to start with. So you can see the importance of digital technology, even if it's not at the forefront. Many of those systems you never even see, you never even know or aware of. That's cool. Personally, I think it's cool, but the example we're going to get to in a minute, how much time I've got, is good, is even cooler. Before I do that, I just mentioned the NHS app. I like this. This picture on the right-hand side is like part of the design for the NHS app when we're designing it. It's part of the service blueprint, we call it. And this is like an example. Before you even get to writing software, there's loads and loads of stuff you can do from all sorts of different walks of life and different backgrounds. Like people involved in this, we have anthropologists that understand how humans interact with each other. We have user researchers that go out there and understand all the digital needs of different people. The NHS app has to work for a digital native as much as it does for somebody who's never used technology in their life and only just got a new phone. How do you make something that's appealing to both those sets of people and everybody else and is easy to use? You've got designers, people who make something look nice but really effective to use at the same time, which is also quite a challenge sometimes. There's just so many different roles. Like personally, I come from a background of university degree in computer science, a kind of classic software engineering background, but there's loads of opportunities to do it otherwise. In fact, we bring on loads of career changers as well. We've even got farmers and things like that have literally changed to software engineering in our business, which is awesome. So, I have chosen to use my main case study to talk about really complex subject. So I'm going to talk about machine learning, and specifically a use case where we've used machine learning to improve the outcomes of IVF, in vitro fertilization. So taking eggs from humans, fertilizing them under a microscope, and then choosing the one that gives the best chance at a baby being born to be reimplanted later. This is a really cool thing. Like the other stuff saves lives, like the stuff I talked about before, the emergency department stuff that literally saves lives. This creates lives. This genuinely helps create more lives than were created before. And I will go into a bit of detail. If anybody's got more questions afterwards, I'd love to talk them through a bit more detail. So, start with what is machine learning. Many people in the audience here today will know what machine learning is, but some people may not, and especially on the video. So I thought I'd describe what machine learning is and steal an example from a famous TV program, Silicon Valley, to do so. So, machine learning, machine learning AI. So machine learning is like AI, we all know AI. I'm going to focus just on machine learning. So teaching a machine to undertake tasks without explicit programming to do so. So it can learn the thing it needs to do, the task it needs to do, and execute that task based on data you send to it. So this is an example for Silicon Valley. The idea being is this is an app that if you take a photo of something, it'll tell you if it's a hot dog or not a hot dog. And what they've done is taken loads and loads of pictures of hot dogs from all different angles, all different types of hot dog, and then loads and loads of pictures that aren't hot dogs, fed it into a computer and iterated over and over again, and that computer has learned from that which features identify a hot dog versus features that aren't hot dogs. And it learns to identify hot dogs, as you can see from the actual app that somebody did develop off the back of that Silicon Valley thing. We can see the hot dog, not the hot dog, although that's quite a cute dog, and hot dog, not hot dog, even though it's got the thing underneath, it's a boot. That is the basic premise of machine learning. Now, it's loads more complex, and I'll touch on some of the complexity in a minute, but these are some examples of where it gets it wrong. We can clearly see why all of those might be considered hot dogs, but they're not hot dogs, but it's thought they were hot dogs. And it just raises a really important point. That is, the machine will learn, but it will also learn a model of what it thinks a hot dog is. And sometimes that internal model it's built will be wrong. It will get stuff right a lot of the time, and it will get stuff wrong. And in a medical setting, if it gets stuff wrong, that might mean lives. That's really important. So just a thing to take away is AI, machine learning, this is to be used in combination with humans, which is exactly what this example of AI does. So hopefully that describes at a very basic level what machine learning is. So we worked with a fertility clinic, the largest one in the UK, with clinics all up and down the country. And they set us an initial challenge. And the challenge was using only image of embryos, eggs, during their development of being fertilized in a lab under a microscope. Can a machine learn to determine which will have the best chance at successful live birth? So in IVF, they will take 10 eggs from somebody, and they will fertilize them all, and they will choose the one or more eggs that they want to implant based on how successful they think it will be. Historically, very experienced people called embryologists with PhDs and huge amounts of experience will do this by eye on a microscope and decide which one to implant. But now with technology, there are algorithms to help them do that, and this was taken to take that one step further. So it's quite a big challenge. It's quite a tough challenge. This literally is cutting edge. It is life creating, and it's basically science. This isn't something you can just go, oh, that's how I'm going to do it. You have to learn, you have to hypothesize, you have to experiment, you have to iterate that over and over again, and you have to decide whether you can actually do it or not. So I thought I'd give an example of the type of data we input into the machines to learn this. The video on the right-hand side is effectively a photograph taken of an embryo under a microscope every 10 minutes for 5 days, sped up in time lapse. So we'll see the evolution of that from 1 cell to 2 cells to 3 cells to 4 cells, all the way to something called blastiosis, which is when it just starts going crazy with cell creation. It's taken, it's taken at 7 different focal lengths. So we see 7 different lengths of focus on the microscope. And that means for each embryo, there's about 5,000 images captured during its life under the microscope. We took 5,200 previous embryos and all their data, all their pictures, and stored a load of others for testing that we'd got it right or not, for testing that we got the model right, and it never saw those ones. And then another important aspect of this is that it goes through those stages. So at the bottom, you can see the stages of embryo evolving. 2 cells, 3 cells. So you've got your first cell creation. 2 cells, 3 cells, 4 cells, 5 cells, 8 cells. I can't remember what all the others mean entirely. Blastiosis. That is what they do. The embryologists will look at it, look at all of them, and they will label the point in time at which each of those things happens, when it changes from the previous to the next. And that's super important because the success of an embryo has been shown to be based partly, obviously there's a lot of aspects of the person, but the embryo itself has been shown to be partly related to the morphokinetic nature. So the speed at which it changes through each of these stages and the shape of each of those stages themselves. So yeah, that's the data. That's a lot of images. To process that requires multiple computers. We use graphics processing units like I've got at home for computer gaming, and quite a few of them. And you literally train it for hours and hours on end, over and over and over again. And it's quite a Herculean effort. So yeah, we started with this live birth prediction. So we gave ourselves about 10 weeks to experiment around this, prove whether we could do it or not. We tried loads of different approaches. For this, we used something called neural networks. Those are kind of a method of deep learning, which is a type of machine learning algorithm that basically kind of uses some knowledge of how neurons in the brain work and their interactions, and implements that in an approach to machine learning. In those 10 weeks, we created a best model that matches their existing approach. So their existing approach was a simple, for those of you mathematicians, simple linear regression based on the speed of change of the egg. That we matched that, but we didn't manage to beat it in that time. And actually, it was quite noisy in the results. So the results would sometimes beat it, sometimes not. And on average, they'd be about the same, but it was too noisy to be considered a success. There's too many extrinsic factors. Like the egg's one thing, but what about the host and all the rest of the other factors? And it was like finding a pattern in a needle in a haystack, basically. Does it even exist? It was and even when you did it, it was very hard to interpret why it had made that decision. It's very like black box. There's very low transparency. So, as all good science does, we changed the problem. The initial challenge was changed. We decided that we should learn from our experiences, not a failure, but a learning, and change the approach we were taking to benefit in a different way. And in this case, we were set a subsequent challenge. Can a machine learn to accurately label the exact moment an embryo changes each stage of development? So at the moment, embryologists do this. It takes them about 2 or 3 minutes for every embryo. They have to do this multiple embryos. And because it's human, there are biases in their decisions. Each of them does it slightly differently. There's little lack of consistency, even though they are absolute experts at this. So if we could do this in an automated fashion, then we could save them a load of time. We could, and they could spend that time on patient care. And then we could feed the results into their existing linear regression. That would then predict live birth chance. And if we got the labels better, we'd improve their existing algorithm, and then we could work on live birth algorithm much later after we'd done that. So this was the plan. How am I doing on time? All right. This was the plan. we call it auto annotation. So we had an even bigger data set for this one, 75,000 embryos with 500 million images in total and 1 million annotations of each change in total. So this is a huge data set. Like that one before is nothing. This is every time you're training this algorithm, it's using 500 million images, high-res images of microscope at 7 focal levels. It's bonkers. And we took a three-step approach using, again, neural networks. So you have to pre-process the image. You have to basically do this. You chop off the bits you don't care about, so you have less data, so you can do it a bit quicker. You shove the focal layers on top of each other. You join them all into one picture, so you get 7 times less data, because otherwise it's just too much data to train it with. And you do a few other bits to tidy it up. Then you classify the images. So you'll say, for every single image, which one of these stages is it? And you'll get something like what you get on the right. So this image, it's 82.04% likely to be 2 cells in that image, right? And you'll choose the one you're most happy with. Problem with that is, that's very good at doing separate images, but it doesn't tell you the point at which it changed from one to the other. And in fact, I didn't include the graph here, but the graph is very fuzzy and it's very difficult to tell which point it changed. So then we have to do a whole analysis of the time series of that information using a separate neural network, totally different architecture for that, called a temporal convolutional network. Unlike the previous one, it's a convolutional neural network. And that would then tell us at the best point at which it changed. And it worked. This one did work. It didn't just work overnight. This took months. It beats the best commercial option out there for doing this. The quality of live birth predictions are at least as good with manual annotations, so it's at least as good as what they have now. Most likely better, but there's not been enough proving of it yet in full. It's transparent. You can see every label it's made, right? You can actually see. In fact, we've built a whole application around this for embryologists, where you see the life of the embryo, you can see the every point at which it's named the change, you can change it, you can disagree with it. It's much quicker to check, but it allows them to check the things they really think they need to check and not check the other ones. And yeah, it does a pretty good job. It's now in action in the clinics all across the UK, and we're looking to improve it further and to work on live birth again. And yeah, that's what the product, like, these are little bits of the product, right? Important point, data science and machine learning, it's not all about the algorithm you create. You can create as good an algorithm as you like, but in this case, you have to change the whole business process through which embryologists work, and you have to embed it into their technology they have today. So they have embryoscopes. They put the 10 embryos in them. They take these photos automatically. We have to integrate with the embryoscope. Once it takes a photo, we have to send it through our model, determine which stage it is, and then at the end of them, we send them all through a time series model. You then have to get all the images out the embryoscope, send them off to a database, and build a whole application around it to do the workflow the embryologists go through, to select the embryos they want to select, to update, change, interfere, and also to see all the stats of what this is labeled in the past. And you can check if it's getting worse or better over time. We call that model drift, for example. Drift is unusual. It's not likely to happen in this circumstance, by the way. Human evolution happens too slowly for data to be a drifting factor. Yeah, this is the app we built, and it's now being used. And that was an example of digital stuff in healthcare. Hope it was interesting.